Hello. I wanted to make a video about learning Objective 8 because the content of the class in Canvas does give you a link to some resources here. So if you go on week 4, there is the Series Approximation with Integral Test, and that's related to learning Objective 8 directly, and that will lead you to this Chimera site, which is really cool and interactive. You can fill in the blanks and kind of follow along. But besides this, there's no actual video that I could find online to link to this work. So I decided to make one myself. Um, so, series approximation is one of the most interesting topics in when learning about series, because if you are using them to estimate something, then you definitely want to know how close is that estimation to the exact answer. If the say your series calculation, is approximating something about a rocket landing on the moon or something, and we want it to be within a certain error, then this becomes quite important. There's type of problems that you will see for learning Objective 8. One is with alternating series, and one is with series that you can apply the integral test to determine convergence or divergence. The alternating series test, there's already some nice videos here. If you go to week 5 module, alternating series error, I think that does a really good job at illustrating that, so I'm not worried too much about it. The one I want to talk about is when we're using the integral test. So, first of all, so whenever you see an alternating series, you know you're going to use the alternating series test. And if you see a sum of positive terms, then you know it's going to be integral test. And so the first thing that you want to do when looking at something where you think, hey, it's going to be integral test, is you want to check the conditions. And I did that in for this second bullet in here where I have the solution written out, but I want to kind of go over that in a video as well. And so first thing is you want to make sure that it's eventually positive. So our sequence here, the terms of our series are 1 over k squared. So the underlying function is 1 over x squared. And this is definitely positive for x is greater than or equal to 1. So eventually positive, that checks. Eventually continuous, yeah, any rational function is continuous. Um, Eventually, and then underlying function, it's eventually decreasing. But eventually, what I mean is that there is some, maybe perhaps even a big x value, that past that x value, the function is always decreasing. So that happens to be 1 in this particular case, but it could be 100, a million, it doesn't matter. As long as for all x's past that one value, the function is always decreasing, always continuous, always positive. You can apply the integral test. There's other ways to check that a function is decreasing, so check that description as well, but I'm going to move on to here. So say we checked all those conditions and it works, and now the goal is, we want to approximate this infinite sum from 1 to infinity, and we want to be using the first 15 terms. So an easy solution would be like, hey, this is approximately equal to 1.58. But if we have a way to bound that error that left over, then we could get a much better handle on much better approximation, as we will see. So this is related to one of the posts that was in the Microsoft Teams, where I think there's a 3 blue 1 brown video explaining why the sum of 1 over k squared is pi squared over 6. I highly recommend you to watch that. So we know the exact answer in this case. But we want to sort of use this as a way to check that we're on the right track because we actually know the answer for this one. But in general, we don't know what it converges to. We know this certainly converges by integral test and p-test, but we don't know what it converges to, what number. And in this case, it's pi squared over 6, but we want to be able to determine a way to approximate this to any within any error that we want. So the goal is then, okay, if I go from k going from 1 to 15, what's left? Well, we're left, from k going from 16 to infinity. That is the error. The sum of the terms starting at 16 going to infinity is the error. And that's the thing that we want to bound. If we can bound that, say between A and B, so if we have, like, in theory, if I know that this sum k going, well, let's just call it error. Yeah, the error is bounded between two numbers A and B. Then when I add it to the original estimation, I can get the full thing because the error in our case is just whatever the infinite sum is, subtracting the estimate of the sum going from 1 to 15. So that's just the sum from 16 to infinity, 1 over k squared. If I know this is from A to B, then I could add up the missing terms in here and get the full infinite series. So I can add up sum from 1 to 15 to all sides of this equation, and that would get me to sum k 1 over k squared plus b. And so adding all that, now I get the full infinite series then from 1 to infinity is between whatever this is. We approximate that. We can do with the computer. We can add the first 15 terms at 1.58. And this 15 is arbitrary, like it could have been 100 if we use the first 100 terms. This same method still applies. Uh, and so then by adding this 1.58 to the A and the B, we have an upper and lower bound for our infinite sum. So we have a way to control, hey, that the answer to this infinite series is between these two numbers. If that's not good enough, then we can crank this up and go to, say, 100 terms and see if that works and helps us solve whatever real world problem we're trying to solve with this infinite series. So this is how it works in practice. We want to bound this summation, and we use integrals to do that. The idea is that if I can visualize this summation of 1 over k squared as a Riemann sum. So if we start at 16 and plug it into the function 1 over x squared, and and we draw a rectangle with a base of 1, the area of that rectangle will be 1 over 16 squared because that's the height, and then the base is 1, so 1 times the height, base times height is the area. So the area of the first rectangle is the first term of that error series, and then we plug in 17, we get the second rectangle area will be um, the second term in that sum, and so on. So we can kind of visualize as the total error here will be the full green area going all the way to infinity here. And so we can use now the integral to estimate it because we already have here, let's use some color. So if I think about the area under 1 over x squared, which is this, right? This is definitely an underestimate of it. So if I go from 16 to infinity, that integral, that will give me the lower bound. There we go. And I know how to find this integral. I can solve this integral. You can find an antiderivative, and then use limits to sort of plug the endpoints and subtract. That's an improper integral. It's not too hard to solve. So we'll do that. We'll do that over here. But then, how about the upper bound? And the upper bound, we want an overestimate. But now you see, there's this little, you know, little like sort of like triangles popping up in here. So we kind of want to put an upper bound on those. So what do we do? Well, the idea is that we can take each of these and kind of imagine like they're kind of like we can cut them on top of the curve here, the 1 over x squared curve, and then we can think about shifting them here um, to this box. And because the function is because the 1 over x squared is decreasing, which is one of the properties that must be true in order for the integral test to be applicable, then we can kind of think of sliding all those in here, and all those blue error areas, they just fill in this little portion of uh, this area under this graph from 15 to 16. So we can see that an upper bound for the sum of the green area will be the integral going from 15 all the way to infinity, because from 16 to infinity is this part, and then from 15 to 16 we get all the blue, an upper bound on all the blue uh, areas that are sticking out. And so going from 15 to infinity, just moving back by 1, gives us an upper bound. That's going to give us a little bit more area. And so now we solve these integrals. And remember, these are improper, need the upper bound to be, you need limits to figure those out. And once you compute those, you plug them in here and then add the 1.58 to everywhere. In here we get the full infinite sum, and voila, we get an upper and lower bound. And you can see that that the actual answer, which is pi squared over 6, it really is within this range. So that kind of verifies that, hey, yeah, we're on the right track in here. It's always good to have some way to check that your work is accurate. In this case, I kind of knew the answer to the whole infinite series, but in practice, you can always use Desmos to help you compute more and more terms to see if whatever answer that you get looks reasonable or not. So I would always do that on a challenge to make sure that, yeah, my solution is I didn't mess up something in there. So so just to recap here, so if I think about the full area, the blue area, that will turn into the upper bound, and that would be the area, the full area from 15 to infinity there. Okay, let's see.